Welcome to the discussion. Today, we're delving into the paper One-Step Diffusion via Shortcut Models, which tackles the computational cost of diffusion models. The authors propose a novel approach called shortcut models to significantly speed up the image generation process. Let's start with the core problem. What makes traditional diffusion models so computationally expensive?
Traditional diffusion models and flow matching models, which are closely related, generate images through an iterative denoising process. This involves many passes through a neural network, each refining a noisy image progressively towards a realistic sample. The number of iterations, often dozens or hundreds, directly impacts the generation time and computational cost. This is the bottleneck the paper addresses.
So the goal is to reduce the number of iterations. How do shortcut models achieve this, and what's the underlying intuition?
Shortcut models achieve this by conditioning the neural network not only on the current noise level time step, but also on the desired step size. The intuition is that instead of taking small, incremental steps in the denoising process, the model can learn to jump ahead by a larger step size, effectively skipping intermediate steps. This is analogous to learning a shortcut path through the noise to data transformation.
That's an elegant concept. But how does the model learn these shortcuts? The paper mentions self-consistency. Can you elaborate on the training process?
The training leverages a self-consistency property. A single large step should be equivalent to a sequence of smaller steps. The model is trained on two objectives. First, a standard flow matching loss at very small step sizes, grounding the model in the correct denoising dynamics. Second, a self-consistency loss for larger step sizes, where the target for a large step is constructed by concatenating the predictions of two smaller steps. This ensures consistency across different step sizes. Crucially, this is all done within a single training phase, unlike many previous approaches.
The paper highlights a comparison with other methods, including distillation and consistency models. What are the key advantages of shortcut models in this comparison?
Shortcut models offer several advantages. First, they are trained end-to-end in a single phase, avoiding the complexity and potential instability of multi-stage training regimes used in distillation methods. Second, they outperform previous end-to-end methods, such as consistency models, which often require careful scheduling and large amounts of bootstrapping. Third, shortcut models offer flexibility. The step size can be chosen at inference time, allowing for a trade-off between speed and quality.
The paper demonstrates results on image generation benchmarks. What were the key findings regarding the quality of the generated images across different step budgets?
The results show that shortcut models generate high-quality images across a wide range of step budgets, from a single step to many steps. Importantly, the quality at many steps matches that of baseline diffusion models, while the quality at few or one step significantly outperforms other methods. This demonstrates the effectiveness of the shortcut approach in drastically reducing computational cost without sacrificing image quality.
Beyond image generation, the paper explores the application of shortcut models to robotic control. What were the results in this domain?
The application to robotic control showed that shortcut policies, replacing traditional diffusion policies, maintained comparable performance with a significant reduction in inference cost, an order of magnitude lower. This highlights the generalizability of the shortcut model approach beyond image generation.
The paper mentions some limitations. What are some of the key challenges or areas for future work?
One limitation is the reliance on an expectation over the data set for the noise to data mapping. This contrasts with other generative models that allow for more direct manipulation of this mapping. Another area for improvement is reducing the gap between the quality of images generated with many steps and those generated with only one step. Future work could explore ways to iteratively refine the noise to data mapping or to improve the one-step generation quality.
The authors provide an open source implementation. What are some best practices for practitioners looking to use shortcut models?
Practitioners should follow standard diffusion model practices, such as normalizing the dataset. If the self-consistency loss is unstable, reducing the ratio of self-consistency targets in the training batch can help. Using a non-zero weight decay is highly recommended, and evaluating with exponential moving average EMA parameters often improves results.
This has been a very informative discussion on shortcut models. Thank you for your insights.